Hi, in this video, I would like to discuss the weighted least squares method. So this is another generalization of least square method. So idea is here. So in some data sets, some observations are more important or more reliable than other observations. So we want to put more weight on those important observations. So the loss function is here, summation of Wj epsilon j square. So Wj is a given constant. So we have to give constant for each observation in some way. So if Wj is larger, the impact of epsilon j square is larger. So that observation is given the more priority. So there are several cases why that we have to put Wj and why we can say Wj is that amount. So example actually from the our data set in this chapter. In Georgia vote data set, a county with more ballots gives a more reliable data point than a county with lesser ballots, right? So because, for example, think about the undercount. We have some factors which affects undercount. Maybe, I don't know, percentage for Gore affects the undercount. But anyway, if the number of ballots is larger, result is more reliable. So think about an extreme case that we only have 10 people in a county. And one undercount is 1/10, 10%. It's very large. If 0 undercount, that is 0. So it's a huge difference, even if just one vote is different. But if we have 10,000 votes in one county, then if we got, for example, undercount of 90 or over 10,000, that is more reliable than this kind of estimate, right? So maybe still some randomness given some predictor values, but still, 95 over 10,000 or 85 over 10,000, that doesn't differ much. So this is more reliable estimate. So this is a typical case, and in statistics, in principle, the variance of the ratio, I mean the ratio is some estimate for some some proportion, for example, the percentage of under ballot. So variance of such quantity is inverse proportional to the sample size. Okay, so basically this comes from the fact that the variance of x1 plus up to xn divided by n is equal to 1/n square summation of variance of xi, and that is the variance of xi over n. So sample size, the variance of the proportion. Proportion is a special case of the sample mean. So the variance of proportion or ratio is proportional to the sample size. So that means if we define the weight Wj is equal to the number of ballots, that is logically correct, the weight. So we can use that weight. Of course, there are some other cases which is good for weighted least square. For example, we have many observations, scientific experiment, but maybe some observations have higher accuracy because of the machine we used. Then we can give more weight on those observations. And if we know the accuracy of the machine, then we can define the weight for each observation. Okay, so this is an R code example for weighted least square. Actually, weighted least square is so common, so LM function already have option to make it weighted least square. So we can specify the weight is equal to something. So this ballots is also a variable in this data set. So in each observation, for each observation, the ballots, the number of ballots is given. So the weight, this should be a vector. This weight should be a vector which have the same dimension as this undercount or percentage Gore or percentage African American. So the result is here. So estimate coefficient, intercept and coefficients for percentage for Gore and percentage of African Americans here, and standard deviation here, and the t-values here. You can remember that the last time the estimation is really vague. Percentage for Gore has very small t-value, and the percentage of African American has the t-value of 0.9. That is insignificant. And even we use robust regression method, the t-value is 1.2. Still, it's not significant. But this time, percentage of African American is very significant, and even percentage of Gore for Gore, negative 0.957. So it's not significant, but at least t-value is not very small. So possibly it is useful information to explain the undercount. Yeah, you can see the previous slide to see the difference. So percentage of African American, both variables have higher t-values. So result is clearer. So why this happens? Because we ignore the less important observations. Okay, we go back to the original figure. So last time when we used robust regression, actually, since we ignored outliers, we put less weight on outliers, the green dots, green points. The result gets slightly better. Remember that. But this time that we give the weight. Actually, we cannot really see the weight here, but probably the truth is that, so these observations, maybe these outliers, but also some of observations which are distant from the regression line or trend line. So these are likely to have the smaller number of, so these come from the county with a smaller number of ballots. Okay, so actually for larger county, probably the most observations are close to this regression line, the true trend line. So that's why when we fit the data, that we get more reliable the estimate for the slope. So the linear trend is clearer if we removed observations of counties with smaller number of ballots. So of course, in statistics, if we use correct method, sometimes the result gets worse or becomes vague. That is possible. But in this case, it works really good. If we used a better method and logically more natural method, then actually we got clearer and strong the conclusion.